Our galaxy hides a violent, predatory history. The Milky Way is not a peaceful island in space, but a cosmic giant with a past built on collisions. By the end of this journey, you will understand how our entire galactic home was forged through ancient acts of consumption. We are going on a deep-time archaeological dig, sifting through fossil stars and ghostly streams to uncover a story of galactic cannibalism. We will trace the evidence from a colossal merger 10 billion years ago to the inevitable future crash with Andromeda. This history did not just shape majestic spiral arms, it may have set the stage for our own existence. What forgotten secrets do you think are still written in the stars above us? This cosmic food chain operates on a scale almost impossible to grasp. At its very top sit galaxies like our own, the undisputed apex predators of their local neighborhood. Their method of growth has a stark and revealing name: galactic cannibalism. It sounds dramatic, and it is, but the process itself is one of slow, gravitational inevitability. Picture not a sudden, violent clash, but a dance of attraction that lasts for eons. A smaller satellite galaxy, bound by the immense gravity of its larger neighbor, begins a long, decaying orbit. Over billions of years, the relentless tidal forces, the difference in gravity's pull between one side of the small galaxy and the other, start to stretch it apart. Stars are pulled from their original orbits, dark matter is stripped away, and the victim's structure unravels into great, shimmering streams that slowly rain down into the halo of the dominant galaxy. Astronomers like Ken Freeman helped us understand that the faint, diffuse glow of a galaxy's halo isn't just empty space. It is a cosmic archive filled with the digested remains of these ancient mergers. This forensic evidence, these stellar fossils and ghostly trails, is what allows us to sit here today and piece together a biography of our Milky Way written in the motions of ancient stars. The dinner was served billions of years ago, but the crumbs are still scattered across our sky, waiting to be read. To read that history, we need a new kind of archaeology. Astronomers today are cosmic detectives, and their crime scenes are light years wide, with evidence scattered across billions of years. Their toolkit is a suite of forensic instruments designed to solve the ultimate cold cases. The premier tool in this investigation is the European Space Agency's Gaia Space Observatory. Think of Gaia as the most meticulous cartographer the universe has ever known. It is not just taking a snapshot, it is creating a dynamic, three-dimensional movie of our galaxy. By measuring the precise positions, distances, and most crucially, the motions of over 1 billion stars, Gaia reveals something astonishing. Against the smooth, predictable flow of the Milky Way's rotation, it finds stars moving together in coherent groups, like schools of fish swimming against a river's current. These are the stellar streams, the dissolving remains of galaxies caught in our gravitational pull. But motion alone is not enough. We need to know where these stars came from. This is where spectroscopic surveys come in, acting as cosmic DNA tests. By analyzing the faint light from a star, scientists can determine its chemical composition, the specific blend of elements forged in its birth cloud. Stars born together in the same galactic nursery share a distinct chemical fingerprint. When we find a group of stars moving together through the halo that also share a unique chemical signature, different from the Milky Way's native stars, the evidence becomes overwhelming. We have found a family, a cluster of survivors from a devoured galaxy. To piece the full story together, researchers then turn to powerful computer simulations. These digital laboratories model the relentless laws of gravity, allowing scientists to rewind time. They can input the current positions and velocities of a stellar stream and run the simulation backward to see what kind of galactic encounter could have produced it. It is the combination of these tools, the precise kinematics from Gaia and the definitive chemistry from spectroscopy, that transforms vague theories into detailed, irrefutable historical narratives. With this forensic power now in hand, we can finally apply it to the Milky Way's most significant and ancient merger, an event that fundamentally reshaped our galactic home. The first major course in our galaxy's ancient feast was served an astonishing 10 billion years ago. Astronomers sifting through the torrent of data from the Gaia Observatory noticed something profoundly strange. When they mapped the velocities of stars, plotting their motions in three-dimensional space, a distinct and unexpected shape emerged. It was not a random scatter, but a coherent, elongated grouping that researchers described with a vivid, almost playful name, the Gaia sausage. This was the ghost in the machine, the telltale signature of a colossal merger. The sausage shape in velocity space revealed the remains of a massive dwarf galaxy, now referred to as Gaia-Enceladus, that had been torn apart and consumed by the young Milky Way. As one of the lead researchers noted in the landmark 2018 papers, this was not a minor event. It was a head-on collision that fundamentally reshaped our galactic home. The energy from this merger likely triggered a huge burst of new star formation, a cosmic baby boom, and contributed the bulk of the stars that make up the Milky Way's inner halo and thick disk. Our galaxy's very architecture bears the scars and gifts of this ancient encounter. It forces us to wonder, if an event this monumental was hidden in plain sight for so long, what other forgotten mergers are still waiting to be decoded from the stellar data flowing in from our telescopes? But the story of our galaxy's past is not just written in the motions of stars. It is painted across the darkness in faint, ghostly brushstrokes. Look up on a clear night far from city lights, and your eyes might trace the hazy band of the Milky Way. Yet hidden within that glow, and arcing far beyond it, are structures of breathtaking subtlety and scale, stellar streams. These are the stretched-out remnants of dwarf galaxies and ancient star clusters, pulled into long, shimmering ribbons by our galaxy's immense gravity. They are the most direct and visible evidence of our galaxy's ongoing appetite. The most spectacular example is the Sagittarius stream, a vast celestial river of stars that wraps around the entire Milky Way like a great, faint loop. This stream is the dissolving signature of the Sagittarius dwarf spheroidal galaxy, a small neighbor currently in the long, slow process of being torn apart and absorbed. For billions of years, our galaxy's tides have been pulling stars away from this dwarf, drawing them out into two great tails that lead and follow it in its orbit. It is a real-time demonstration of galactic cannibalism, a process so slow that from our perspective, it appears as a frozen moment, yet one whose outcome is inevitable. These streams are far more than just pretty relics. They are dynamic tracers, sensitive probes of the invisible universe. The very shape of a stellar stream, its density and how it bends, tells a profound story. As the stream orbits, it feels the gravitational pull of everything the Milky Way contains, including the vast, unseen halo of dark matter that envelops us. By studying the stream's distortions, astronomers can essentially map the distribution of this mysterious substance, weighing our galaxy in a way that would otherwise be impossible. Sophisticated computer visualizations show this evolution, depicting how a tight cluster of stars is gradually smeared into a delicate filament over cosmic time. The presence of so many streams, from the massive Sagittarius to dozens of fainter ones now being discovered, reveals a crucial truth. Our galaxy's history is not just one of a few colossal mergers, but of a steady diet of smaller snacks. Each faint ribbon in the halo is a ghost of a past encounter, a silent witness to the dynamic and often violent ecology that built the familiar spiral we call home. While the Sagittarius stream is a spectacular showpiece, other relics in our halo tell quieter, older stories. One of the most fascinating is known as the Helmi stream, a group of stars discovered not by their brightness but by their peculiar motion. Back in the late 1990s, astronomers analyzing early stellar surveys noticed something odd. A handful of stars scattered across the sky were not moving with the general flow of the Milky Way's disk. Instead, they traced a highly inclined, looping orbit, diving high above the galactic plane and then plunging far below it. It was as if these stars were marching to the beat of a different, long-forgotten drum. Their shared, unusual path was the first clue that they were a family, survivors from a common origin. Further study revealed their chemical signature, and it spoke of ancient beginnings. These stars are metal-poor, meaning they contain very low amounts of elements heavier than hydrogen and helium. In cosmic terms, metals are forged in the hearts of stars and scattered by supernova. A metal-poor population indicates a birthplace in a small, primitive galaxy that lived and died early in the universe's history, before many generations of stars could enrich it with heavier elements. The Helmi stream, therefore, is not a recent acquisition. It is the remnant of a dwarf galaxy that was drawn into and assimilated by the Milky Way between 5 and 8 billion years ago, a fossil from a much younger cosmos. What makes this case so instructive is its trajectory. This ancient galaxy did not come in on the same plane as our disk. It struck from a different angle, adding its stars to the halo in a unique, looping pattern. This demonstrates a crucial point. Our galaxy's growth was not a neat, orderly process. It was a messy accumulation of mergers from all directions, each event depositing its stellar debris with a distinct motion and chemistry, like different layers of sediment in an archaeological dig. The Helmi stream stars have maintained their shared motion for billions of years, a kind of family accent preserved across cosmic time. Their very existence, identified purely by their motion against the galactic background, encourages a thrilling thought. As surveys like Gaia grow more detailed, how many more of these faint, fossilized families are waiting to be recognized, each holding a piece of the puzzle of how our galaxy was built? The giant redwoods of California stand as silent witnesses to the passage of millennia, their growth rings recording centuries of history. In a similar way, another ancient merger left its own indelible ring within the stellar population of our galaxy, earning it the evocative name, the Sequoia event. This proposed merger represents another foundational pillar in the Milky Way's construction, a distinct chapter of accretion that scientists are only now learning to read. The evidence comes once again from the subtle language of motion and chemistry. Researchers analyzing Gaia data identified a group of stars on highly eccentric, plunging orbits, a signature of a dramatic past encounter. Their chemical makeup tells a story of an independent origin, born in a separate, smaller proto-galaxy that met its end within our own. Current estimates place this merger around 9 billion years ago, a time frame that intriguingly overlaps with the colossal Gaia-Enceladus collision. This overlap is at the heart of a fascinating scientific debate. Are the Sequoia stars and the Gaia Sausage stars the remains of two separate galactic building blocks that fell in at roughly the same cosmic epoch? Or are they different dynamical families from the same single cataclysmic merger event, their orbits sorted by the chaotic forces of the collision? Distinguishing between these ancient accretion events is like trying to separate the sediments from two different rivers that flowed into the same lake billions of years ago. The particles have mixed yet subtle differences in their composition might tell them apart. This is precisely where galactic archaeology shines as a living, evolving science. Each new data release from missions like Gaia, each deeper spectroscopic survey, acts like a more powerful microscope. What looked like a single population of halo stars a decade ago now begins to resolve into distinct families with their own unique histories. The very fact that we are having this debate, that names like Sequoia and Gaia-Enceladus are proposed and scrutinized, shows how rapidly our picture of the Milky Way's youth is coming into focus. It is a reminder that our galactic history is not a settled textbook narrative, but a dynamic detective story being written in real time. If two such major events are still being passed from the stellar fossil record, what other named mergers currently hidden within the data await their moment of discovery? But to truly understand the dawn of our galaxy, we must look even further back into a time so distant that the evidence becomes ghostly and the science turns into a form of cosmic speculation. This brings us to one of the most intriguing and hypothetical figures in our galactic ancestry, a proposed merger so ancient it has been given the mythical name, the Kraken. In the digital laboratories where astrophysicists build universes, a fascinating pattern emerges. When scientists run sophisticated computer simulations to grow a Milky Way-like galaxy from the primordial soup of the early universe, the models often suggest a dramatic beginning. They predict that before the Gaia-Enceladus merger, before even the Sequoia event, our young galaxy may have consumed another truly massive dwarf galaxy, a Kraken, in the first few billion years after the Big Bang. The challenge is staggering, an event that would have happened when the galaxy was still a chaotic, forming cloud of gas and stars. The stellar debris from such a merger would have been churned and mixed for over 10 billion years, spread so thoroughly throughout the galactic halo that its distinctive chemical and kinematic signature is all but erased. Finding evidence is like trying to identify a single river that flowed into the ocean at the dawn of time, its waters now completely blended with the global sea. So how do we search for a ghost? We look for the echoes it left in the things that survived. Researchers sift through the data of the oldest, most metal-poor stars in the halo, searching for subtle statistical groupings in their motions or their elemental abundances that don't fit the patterns of later mergers. It is a painstaking process of elimination, a quest to find the foundational layer beneath all the other layers we have already identified. The very idea of the Kraken highlights a profound shift in our approach to galactic history. We are no longer just reconstructing the past from obvious clues. We are now using the predictive power of theoretical models to guide our search, telling us where and what to look for in the overwhelming stellar census. This is the cutting edge of galactic archaeology, where simulation and observation engage in a continuous dialogue. The models make a prediction, the observers scour the data for hints, and their findings then refine the next generation of simulations. It is a detective story that pushes the boundaries of what we can know, forcing us to ask if our galaxy's infancy was shaped by a titanic encounter with a Kraken. What indelible mark did that first, defining feast leave on the character of the Milky Way we inhabit today? This chemical fingerprint is the true birth certificate of a star. While motion tells us where a star is going, its chemical composition tells us where it came from, a story written in the faint light of its atmosphere. Every star forms from a cloud of gas, and that cloud carries a specific blend of elements forged in previous generations of stars. Stars born from the same natal cloud, in the same region of a galaxy, will share that unique chemical signature, like siblings sharing distinct family traits. This is the principle of chemical tagging, and it transforms starlight into a readable history book. By analyzing a star's spectrum, the rainbow of light it emits split into fine lines. Astronomers can measure the precise amounts of elements like iron, magnesium, and silicon. The ratio of these elements, particularly what are called alpha elements to iron, acts as a cosmic clock and a galactic ID card. A high alpha to iron ratio typically points to a galaxy that formed stars rapidly and violently, in short, intense bursts, often the hallmark of smaller, ancient dwarf galaxies. A lower, more balanced ratio suggests a more extended, quieter history of star formation, like that in the main disk of the Milky Way. To gather this chemical data on a galactic scale, massive spectroscopic surveys have become essential. Projects like APOGEE, which uses a telescope in New Mexico, and GALAH, based in Australia, operate like cosmic DNA testing facilities. They don't just look at a few stars, they systematically collect the spectra for hundreds of thousands, even millions, of stars across the sky. This creates a vast chemical census of our galaxy. When astronomers cross-reference this chemical data with the kinematic maps from Gaia, the power of this approach becomes stunningly clear. They can now find a stream of stars moving together and confirm they are a true family by showing they share the same distinct chemical fingerprint, one that differs markedly from the native Milky Way population around them. But the story goes even deeper. That unique chemical pattern is more than just an identifier. It is a detailed profile of the galaxy that star was born in. From the abundances of different elements, scientists can infer the mass of the devoured galaxy, estimate how long it formed stars, and even piece together the tempo of its star formation history. It allows them to reconstruct not just the fact of a merger, but the character of the lost galaxy itself. Was it a small, primitive dwarf that lived fast and died young, or a more substantial building block with a complex life of its own? Chemical fingerprinting adds rich, personal detail to the broad strokes of gravitational history, letting us hear the individual voices within the chorus of the halo. Yet all of this violent history, the stretching of streams and the churning of orbits, depends on a force we cannot see. The true architect of galactic cannibalism is not the stars themselves, but the invisible sea in which they swim, dark matter. Every galaxy, including our own, is embedded within an immense, diffuse halo of this mysterious substance that extends far beyond the last visible star. Think of a galaxy not as a flat disk of light, but as a glittering chandelier suspended within a vast, invisible room. The shape and size of that room, the dark matter halo, dictates everything. It is this halo's immense gravitational pull that first captures passing dwarf galaxies, sealing their fate. The trajectories of the stellar streams we see today, those graceful arcs of orphan stars, are not random. They are precise tracers, sensitive probes bending under the influence of the halo's unseen mass. By meticulously mapping how a stream like Sagittarius curves and twists, astronomers can essentially perform a gravitational autopsy. They can weigh the Milky Way's dark halo, measure its density at different distances, and even infer its overall shape. Is it a perfect sphere, a flattened football, or something more lopsided? The streams tell that story, turning the tragic debris of past mergers into a powerful tool for illuminating the invisible architecture of our home. This relationship between dark matter and mergers is a two-way street. Just as the halo dictates the merger reshapes the halo. Sophisticated computer simulations reveal a dynamic dance. When a sizable dwarf galaxy plunges into a larger one, it doesn't just donate its stars. Its own small dark matter halo also merges with the larger one, and the incredible energy of the collision can churn and redistribute the invisible material. Theoretical work suggests that repeated major mergers can actually make a dark matter halo more spherical and puffy over time, smoothing out its original form. This means the violent history we are uncovering did not just build the visible galaxy we see, it also sculpted the unseen gravitational landscape that now cradles it. To truly comprehend the full mechanics of galactic consumption, we must understand this dark scaffolding. It is the ultimate stage upon which the cosmic drama of creation and destruction has played out for billions of years. A silent, pervasive force that guides every act of cannibalism and every stream of stellar light we now use to read its past. This painstaking work of cosmic reconstruction has a name: galactic archaeology. It is a field that transforms astronomers into time travelers, sifting through the galactic halo as if it were a vast archaeological dig. In this grand excavation, individual stars are the artifacts, each one holding clues about the era and place of its birth. Their precise motions through space, meticulously charted by observatories like Gaia, serve as historical records, preserving the gravitational echoes of ancient encounters. Their chemical compositions read like inscribed tablets of elemental data, tell unambiguous stories of their original homeland. The overarching goal of this entire endeavor is staggeringly ambitious: to construct a coherent timeline of our galaxy's assembly, from its first fragmented beginnings to the majestic spiral we inhabit today. This work beautifully bridges two vast scales of cosmic science. On one hand, it connects to cosmology, the study of the universe's largest structures and its origin in the Big Bang, which provides the initial conditions from which galaxies like ours emerge. On the other, it relies on stellar astrophysics, the detailed study of how individual stars live, die, and forge new elements. Galactic archaeology sits precisely in the middle, using the life stories of billions of individual stars to decode the biography of an entire galaxy. It is a holistic view that treats the Milky Way not as a static portrait, but as a dynamic, layered history book. By reading its pages, we prepare ourselves for the most profound question of all: how did these violent, ancient acts of creation and consumption directly shape the specific galaxy, and even the specific neighborhood within it that allowed our own story to begin? These ancient collisions were not merely destructive acts, they were creative forces. The very shape of our galaxy, its majestic spiral arms and its central bulge, bear the imprint of those violent encounters. When a dwarf galaxy plunges into a larger one, it delivers an immense infusion of energy. It shakes the very fabric of the galactic disk, sending powerful shockwaves through its reservoirs of gas and dust. This chaos has a profound consequence. It triggers dramatic bursts of new star formation. Imagine a stone thrown into a still pond. The ripples churn the water. In a galactic merger, those ripples compress vast clouds of gas, causing them to collapse under their own gravity and ignite into brilliant clusters of new stars. This is how a seemingly destructive event becomes a cosmic nursery. The colossal Gaia-Enceladus merger, for instance, is believed to have delivered not just stars but a torrent of fresh gas. The gravitational turmoil from that head-on collision likely fueled an epoch of intense stellar birth, contributing significantly to the formation of two key structures: the Milky Way's central bulge and its thick disk. The thick disk is that puffy, older population of stars that surrounds the thinner, brighter plane we see at night. It is a fossilized record of that ancient period of vigorous, merger-driven creation. So did these events create the beautiful spiral arms we see today? Not directly. Our current spiral structure is thought to be governed by internal density waves, like a traffic jam moving through the stars and gas of the disk. But the raw material for those future stars, the gas accreted during mergers, is absolutely essential fuel. This transforms our view entirely. Galactic cannibalism is not just a story of consumption, it is a story of recycling and renewal. The victims of these ancient encounters did not vanish without a trace. Their very substance was woven into the evolving tapestry of the Milky Way, becoming part of its bones and its breath. This leads to a final, intriguing question about the ultimate fate of these consumed galaxies. If a dwarf galaxy had a central black hole, a tiny dark heart, what happened to it when its home was torn apart? But what of the very hearts of those devoured galaxies? If a dwarf galaxy had a central supermassive black hole, a tiny, dense engine of gravity, what became of it when its home was torn apart? This question adds a hidden, compact layer of drama to our already epic story. It is true that many larger dwarf galaxies likely did host their own central black holes, though these would be far smaller than the 4 million solar mass giant at the center of our own Milky Way, Sagittarius, a star. They might be mere thousands or even just hundreds of thousands of times the mass of our Sun, but they are gravitational powerhouses nonetheless. during a galactic merger, the fate of these wandering black holes is a cosmic game of gravitational pinball. One possibility is that they are simply ejected, flung out into the dark, lonely reaches of the galactic halo. As the stars of their host galaxy are stripped away, complex gravitational interactions between multiple bodies can act like a slingshot, booting the black hole clear of the merging chaos. It would then drift through the darkness, an invisible, massive ghost, perhaps accompanied by a small, tight cluster of stars that manage to stay bound to it. Another equally fascinating fate is that they sink. Dragged by dynamical friction against the background of stars and dark matter, these black holes could slowly, over billions of years, spiral inward toward the very center of the Milky Way. There, they might eventually merge with our own central supermassive black hole, or perhaps orbit it in a slow, silent dance. We have hints that such an outcome is possible. Some observations suggest our galactic center might host not one, but several black holes in a crowded neighborhood. The search for evidence of these wanderers takes clever, indirect forms. One method looks for hypervelocity stars moving so fast they are unbound from the galaxy entirely. While some are flung out by interactions with our central black hole, others could have received their incredible kick from a close encounter with a smaller, wandering black hole during the chaotic merger process. Finding a star racing away from an unexpected location in the halo could point to the invisible culprit that launched it. The most definitive proof, however, may come not from light, but from ripples in space-time itself. Future space-based gravitational wave observatories will be sensitive to the mergers of these intermediate mass black holes. The faint chirp of such a collision, detected from the depths of our halo, would be the ultimate confirmation, a direct signal from one of the most dramatic and hidden consequences of our galaxy's violent appetite. It means the story of galactic cannibalism is not just written in streams of stars, but in the silent, invisible motions of the most extreme objects the universe can create. Our largest galactic companion is not just a neighbor, it is a future meal. The large Magellanic Cloud, that hazy smudge of light visible from the southern hemisphere, has long been viewed as a serene satellite orbiting our Milky Way. Recent discoveries have dramatically rewritten that peaceful story. We now understand this cloud is far more massive than we ever guessed, and it is not a long-time orbital companion. It is a first-time visitor caught in the act of falling toward our galaxy for the very first time. This transforms the large Magellanic Cloud from a backdrop object into the protagonist of our galaxy's next major chapter of growth. Measurements from orbiting observatories have revealed its true heft, containing perhaps 10 or even 20% of the Milky Way's own visible mass. That is not a small satellite, that is a substantial galactic building block in its own right, and it is moving. It is on what astronomers call its first infall, a single, fateful trajectory that will eventually bring it into a long, decaying dance with our spiral home. We are witnessing the opening act of a merger that will play out over the next several billion years, a rare opportunity to observe the prelude to a cosmic collision in real time. The effects are already being felt. The immense gravity of the large Magellanic Cloud is so strong it is not just a passive passenger, it is an active disturber. As it plows through the outskirts of our galaxy's halo, its pull is warping and twisting the very fabric of the Milky Way's outer regions. Computer simulations show this vividly, depicting how the invisible dark matter halo and the sparse outer stars are being tugged out of shape by the cloud's passage. Even more intriguing, it appears to be dragging its own entourage. Several of the tiny, ultra-faint dwarf galaxies that orbit the Milky Way are not orbiting us at all. They are following the large Magellanic Cloud. They are its own satellites, caught in its gravitational wake and being pulled along for the ride into their eventual dissolution within our galaxy. This presents an unprecedented live case study. For the first time, we can watch the initial stages of a major accretion event. studying how a large dwarf galaxy begins to interact with and distort its giant host long before the final destructive merger occurs. We are seeing the first gentle tugs that will, over epochs of time, unravel into streams and ignite new waves of star formation. The Large Magellanic Cloud is a gift to galactic archaeologists, a chance to calibrate our models of the past by observing the present. It makes you wonder what subtle changes in the motions of distant stars today are the earliest whispers of this future feast, clues that we are only now learning how to hear. There is no better example of this slow cosmic digestion than the Sagittarius dwarf spheroidal galaxy. We are not looking at ancient history here, we are witnessing a galactic meal in progress. This small companion was only discovered in the early 1990s, a faint smudge of light hidden behind the dense star fields of our own galactic bulge. Its very detection was a triumph, revealing a neighbor being consumed right before our eyes. At its heart, a dense core of stars still holds together, orbiting the Milky Way on a polar path that takes it plunging directly through our galactic disk. But with each perilous passage, the Milky Way's immense gravity exacts a toll. Like a planet orbiting too close to its star, the dwarf galaxy is being tidally stripped. Great swaths of its stars are being pulled away, not in a single violent event, but in a steady, relentless gravitational rain. This is the source of the magnificent Sagittarius stream, that great loop of stars encircling us. The stream is not a static monument, it is an active river of stellar debris flowing from the dwarf as it slowly disintegrates. Sophisticated computer models chart this fate with chilling clarity. They show the dwarf's trajectory over the next several 100 million years, a decaying orbit that will see it loop around the Milky Way again and again. With each orbit, more of its substance is peeled away, its core growing ever smaller and more diffuse. The simulations predict that within roughly 1 billion years, the process will be complete. The Sagittarius dwarf will cease to exist as a coherent galaxy. Its remaining stars will have fully joined the Milky Way's halo, and its dark matter will have blended with our own. This real-time observation transforms an abstract theory into a visceral reality. We can point to a specific patch of sky and say, there, a galaxy is dying. Its stars are being methodically catalogued into our own. This is the ultimate case study in galactic cannibalism, a slow-motion demonstration of the gravitational tides that have shaped our home since its birth. The fate of the Sagittarius dwarf is not unique. It is simply the most visible and advanced example in our sky. It is a preview of what ultimately awaits every small galaxy that wanders too close to a giant, a solemn reminder of the dynamic, often unforgiving ecology that governs the universe on the grandest scales. All of these ancient encounters have left their remains scattered throughout a vast, silent volume of space that envelops our entire galaxy. This is the galactic halo, a spherical cloud of ancient stars, mysterious dark matter, and dense globular clusters that extends hundreds of thousands of light years in every direction. If the Milky Way's brilliant disk is its vibrant, living heart, then the halo is its memory, a cosmic cemetery and mosaic where the debris of consumed galaxies is laid to rest. It is not a smooth, uniform shell. Instead, it is a profoundly lumpy and complex structure, filled with the overlapping signatures of countless mergers. Within this sphere, astronomers make a crucial distinction between two populations of stars. The first are known as in situ stars, meaning they formed in place from the primordial gas that collapsed to create the infant Milky Way itself. The second, and for our story the most important, are the accreted stars. These are the immigrants, the survivors from dozens of smaller galaxies that were drawn in, torn apart, and their stellar citizens scattered across the halo. Telling these populations apart is the central challenge of galactic archaeology, because the halo's very structure encodes the entire assembly history of our home. Its lumpiness, the density of stars in one region versus another, the specific motions and chemistries of its inhabitants, all of this data forms a three-dimensional fossil record. By meticulously mapping this record, scientists are not just listing past events, they are reconstructing the sequence and timing of our galaxy's growth, like determining the order in which layers of sediment were deposited in a geological formation. The ultimate goal is to create a complete family tree for the Milky Way, to name every major progenitor galaxy and understand what each one contributed. With every new stellar stream discovered and every faint cluster of stars chemically tagged, that family tree grows more detailed and more surprising. It forces a humbling question as our telescopes peer deeper into this sparse stellar fog. How many more of these ghostly fragments, these pieces of lost galactic identities, are still waiting to be mapped and given their rightful place in our origin story? Scattered throughout that vast, silent halo are dense, glittering islands of stars, globular clusters. These ancient, spherical swarms each contain hundreds of thousands of stars, all bound together in a tight gravitational embrace. For a long time, they were seen simply as part of the Milky Way's native population, beautiful but permanent fixtures. We now know that many of these stellar jewels are not native at all. They are stolen treasures, celestial heirlooms ripped from the grasp of devoured galaxies during those ancient mergers. Their survival tells a fascinating story about the range of possible outcomes when galaxies collide. While a dwarf galaxy's loose outer stars are easily torn into streams, its densest core regions, like these globular clusters, can sometimes hold together against the tidal forces. They are carried into the Milky Way's halo almost intact, like a ship's sturdy cargo surviving a storm that sinks the vessel itself. To confirm their foreign origin, astronomers again turn to the dual languages of motion and chemistry. Many globular clusters, especially those in the outer halo, follow highly eccentric, plunging orbits that are completely different from the orderly paths of the Milky Way's native clusters. They are moving like interlopers because, in fact, they are. Their chemical fingerprints provide the final proof, showing elemental abundances distinct from stars born in our own galactic neighborhood. The most spectacular example is the magnificent Omega Centauri, the brightest globular cluster in our sky. It is an outlier in almost every way, far more massive and complex than a typical cluster. For decades, its unusual nature sparked a compelling theory that Omega Centauri is not a true globular cluster at all, but the stripped core of a dwarf galaxy that was almost entirely consumed. The stars at its very center move in a way that suggests the presence of a substantial intermediate mass black hole, exactly the kind of dark heart a small galaxy might possess. This makes it a unique time capsule, a surviving nucleus from a lost galactic building block, now orbiting our own as a glittering trophy of a long-finished cosmic conquest. For scientists, these kidnapped clusters are a gift. They provide a discrete, manageable sample of stars that all form together in the same foreign environment, a clean snapshot of chemical conditions in another galaxy. By studying them, we gain a direct, uncontaminated look into the stellar populations of the Milky Way's ancient victims, without having to sift through the mixed debris of the entire halo. Their very existence, these dense balls of light surviving billions of years after their parent galaxy was destroyed, highlights the complex and varied results of galactic cannibalism. It was not always a process of total annihilation. Sometimes the most resilient and beautiful pieces were preserved, orbiting us now as eternal reminders of the galaxies that once were. To test these theories, we need a laboratory the size of the universe. Since we cannot rewind time and watch our galaxy form, astronomers have built the next best thing inside the world's most powerful supercomputers. These are not simple animations, they are staggeringly complex digital universes, governed by the exact same laws of physics that shape reality. Scientists begin by creating a virtual box of space, then filling it with the ingredients prescribed by our best cosmological models, a cosmic web of dark matter and primordial gas. They set the initial conditions to match the universe just after the Big Bang, and then they press play. Gravity takes over. Over millions of CPU hours, the simulation calculates the interactions between billions of particles, watching as dark matter clumps into halos, gas cools and condenses to form stars, and small structures merge to build larger ones. The goal is to grow a digital twin of a Milky Way-like galaxy from the ground up. This virtual laboratory allows for a kind of cosmic experimentation that is otherwise impossible. Researchers can run the simulation thousands of times, each time slightly altering the starting parameters or the sequence of merger events. They can watch, in exquisite detail, how a dwarf galaxy is torn apart by tidal forces, how its stars are scattered into streams, and how those streams twist and fold over billions of years within the halo of the larger galaxy. The predictive power of these simulations is what makes them so invaluable. They don't just recreate what we already see, they tell us what to look for next. A simulation might predict that a merger with a galaxy of a certain mass on a certain trajectory will produce a stellar stream with a very specific shape and orbital pattern. Astronomers can then take that prediction and scour the Gaia data, searching the real sky for a stream that matches that exact signature. When they find it, it is a moment of profound validation, a direct link between theory and observation. This iterative process, this constant dialogue between the digital universe and the telescope's eye, is how our understanding is refined. The simulations provide the narrative framework, the possible storylines for our galaxy's past. The real-world data from Gaia and spectroscopic surveys provides the evidence, confirming which of those storylines actually happened. It turns the chaotic fossil record of the halo into a decipherable history. Without these digital twins, we would be like archaeologists with a field full of shattered pottery, but no idea how the pieces fit together or what the original vessels looked like. The simulations give us the blueprint, allowing us to reconstruct the galaxy not as it is, but as it was, one virtual merger at a time. This universal process of assembly is written into the very laws of the cosmos. Our current best model of the universe, known as the lambda-cold dark matter model, provides the grand script. It tells us that structure in the cosmos grows hierarchically from the bottom up. Small clumps of dark matter and gas form first, then merge to build larger and larger structures over time. In this framework, every large galaxy like our own is not born whole, but is assembled piece by piece through a long history of mergers and acquisitions. It is the fundamental way galaxies grow. So, if this process is universal, does that make the Milky Way's violent history ordinary? Is our story just one copy of a common cosmic template? The answer is both yes and no. The process is indeed the rule, but the specific biography of each galaxy is wonderfully unique. Consider our nearest large neighbor, the Andromeda Galaxy. Through deep observations, astronomers have found that Andromeda's outer halo is a chaotic mess, littered with stellar streams and shells that tell a tale of even more recent and dramatic mergers than our own. It appears Andromeda has been a more voracious and active cannibal over the last few billion years, consuming several sizable dwarf galaxies and leaving its halo in a state of greater turmoil. Our own galactic halo, by comparison, seems more settled, its most colossal feasts occurring in the more distant past. This difference is not an error in the model, it is the model in action. Each galaxy's history is shaped by the specific sequence of mergers it experiences, the masses of its victims, the angles of their collisions, and the timing of it all. Think of it like the life story of any individual. While all humans share common experiences of growth and change, the particular events of your life, the order they happened, and the people you met along the way make your personal history one of a kind. The Milky Way is no different. Its unique combination of the ancient Gaia-Enceladus merger, the ongoing digestion of Sagittarius, and the impending arrival of the large Magellanic cloud gives it a distinct personality in the galactic neighborhood. This uniqueness is precisely what makes our home so scientifically precious. Because we are inside it, we can study its history in unparalleled detail, measuring the motions and chemistry of individual stars in a way we simply cannot do for any other galaxy. The Milky Way thus becomes the foundational benchmark, the Rosetta Stone for galactic archaeology. By deciphering our own story with such precision, we calibrate our models and our interpretations of the fainter, more distant galaxies we see across the universe. Our galaxy's biography is more than just local history. It is the key chapter against which we read the entire cosmic narrative of how islands of stars are born, live, and evolve across time. The ultimate chapter in our galaxy's story has already been written, but its final pages will not turn for billions of years. Our entire galactic neighborhood is on a slow, inescapable collision course. The Hubble Space Telescope has delivered precise measurements that settle a long-standing question. The Andromeda Galaxy is not merely drifting in our general direction, it is heading straight for us. In roughly 4.5 billion years, the two great spirals will meet. This will not be another story of a giant consuming a dwarf. This is a head-on merger of equals, a transformative event that will rewrite the cosmic map. The process will unfold over an almost incomprehensible timescale, a drawn-out celestial dance lasting perhaps 2 billion years from first close approach to final coalescence. As the galaxies draw near, their mutual gravity will begin to warp and distort their beautiful spiral structures, pulling out vast, luminous tails of stars and gas. The skies from any hypothetical future planets would become unimaginably spectacular, filled with the looming shape of the approaching galaxy, a tapestry of new stars being born from colliding gas clouds, and a night sky strewn with unfamiliar constellations as stellar orbits are thrown into chaos. Yet for all this apparent violence, the likelihood of actual stellar collisions is remarkably low. The distances between stars are so vast that they will mostly pass by one another like ships in an immense, dark sea. The real action is in the gravitational turmoil, which will churn and mix the two galaxies into something entirely new. The result of this colossal merger, often playfully nicknamed Milkdromeda, is predicted to be an elliptical galaxy, a featureless, football-shaped swarm of stars. This future form stands in stark contrast to the graceful spirals we know today, marking a fundamental shift in galactic type. This is the key difference from the past acts of cannibalism we have explored, where the Milky Way's identity remained largely intact as it absorbed smaller victims. The collision with Andromeda is not an act of consumption. It is an act of synthesis, a true transformation where both original identities are lost to create a single, new entity. It serves as a profound reminder that the dynamic, evolving universe we see today is not a finished product. The saga of galactic evolution is an ongoing epic, with its most dramatic acts still waiting in the distant wings of time. But if galaxies are built from mergers, where did the other pieces go? This line of questioning pushes galactic archaeology into its most ambitious frontier, the search for our galaxy's long-lost siblings. We know the Milky Way consumed smaller galaxies, but those victims themselves had histories. They formed from the primordial gas of the early universe. They lived their own lives, and they may have even consumed smaller galaxies of their own before they were, in turn, consumed by us. This idea transforms our halo from a simple graveyard into a tangled family reunion, where the stars around us carry ancestry from multiple, nested layers of galactic lineage. The ultimate goal is no less than to write a complete family tree, a galactic genealogy that traces the lineage of every star in the halo back to its original host protogalaxy. The challenge is staggering, like trying to trace the ancestry of every person in a modern nation back to specific, ancient tribes whose records have been lost to time. Once a dwarf galaxy is fully assimilated, its stars are churned and mixed for billions of years. Their unique motion as a group is erased by countless gravitational interactions, leaving only their shared chemical fingerprint as a clue. But even that fingerprint can be blurred if the victim galaxy itself had a complex history of star formation. So how do we begin? Scientists are turning to a powerful combination of immense data and statistical inference. Instead of trying to identify individual stars from a specific named galaxy like Gaia-Enceladus, they use advanced computer models to simulate the entire formation of a Milky Way-like galaxy. These simulations track not just where stars end up, but where they began. Researchers can then compare the statistical properties of the stars in their simulated halo, their distributions of motion, energy, and chemistry, with the vast datasets we now have from Gaia and spectroscopic surveys. It is a process of matching patterns. If the real halo shows a statistical excess of stars with a certain combination of orbital energy and chemical makeup, and that pattern matches a specific population of accreted stars in the simulation, then we can infer that a progenitor galaxy with those properties was consumed. This method allows astronomers to move beyond the obvious, recent mergers like Sagittarius and begin quantifying the contributions of older, more thoroughly mixed building blocks. It is a bit like hearing a complex symphony and trying to identify not just the loudest instruments, but the subtle contributions of every section that have blended into the overall sound. This work represents the cutting edge of the field, an attempt to move from reconstructing a few major events to writing a complete biographical ledger for our galaxy. It asks a profound question: if we could read the genealogy of every star above us, how many distinct galactic lineages would we find woven into the tapestry of the Milky Way? The atoms that make up our world carry a memory of those ancient collisions. Could the violent mergers that built our galaxy have also set the stage for life itself? It is a profound and speculative question, one that ties our own existence to the grandest cosmic events. While we cannot draw a direct line of cause and effect, the connections are deeply suggestive. Consider the aftermath of a major merger like the Gaia-Enceladus event. The immense gravitational energy would have triggered furious waves of new star formation, a starburst. In those short-lived, massive stars, nuclear furnaces worked at a frantic pace, forging heavy elements like carbon, oxygen, and iron. When these stars ended their lives in spectacular supernova, they seeded the surrounding gas clouds with these essential ingredients. This enriched interstellar medium, this cosmic fertilizer, later condensed to form new generations of stars, but now surrounded by the dusty debris needed to build rocky planets like Earth. The very elements that form our bones, our oceans, and our air were created in stars, and the mergers that shook the galaxy may have been the catalyst that spread those elements far and wide. Could it be that the gravitational jolt from a passing dwarf galaxy even played a role in our own solar system's birth? Dense molecular clouds, the nurseries of stars, can exist in a quiet equilibrium for eons. A significant disturbance, a ripple from a galactic merger passing through, might have been the nudge that caused a particular cloud to collapse, triggering the chain of events that led to the formation of our Sun and its planetary disk. It is a captivating thought that our most local origins might be linked to the most distant galactic history. While we may never find a specific merger and label it the reason we are here, the overarching narrative is clear. The Milky Way's growth through cannibalism was not a sterile process. It was a creative and enriching one. It stirred the galactic pot, mixing stellar material from different origins and driving the chemical evolution that made complex chemistry, and thus life, possible. We are, in a very literal sense, children of that mixed heritage. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in stars that lived and died long ago. Some of those stars may have been born in the original Milky Way, while others were citizens of galaxies like Gaia-Enceladus or the Kraken, their substance donated to our galaxy during its violent youth. We are the product of a unified cosmic ancestry, a living testament to the fact that the universe builds complexity and even life through processes of collision and union. Our galaxy's violent history may hold the key to a deeper cosmological puzzle, one that pits our theories about the universe's smallest structures against the hard evidence in our sky. This is known as the missing satellite problem. According to our most successful models of dark matter and cosmic evolution, the vast halo of our Milky Way should be teeming with hundreds of small, faint dwarf galaxies, each one a tiny clump of dark matter with a sprinkling of stars. Yet when we look, we only see a few dozen. So where did all those predicted satellites go? One compelling answer brings us right back to galactic cannibalism. Perhaps they are not missing at all, but were simply consumed long ago. The relentless appetite of our young galaxy could have devoured a vast population of these primordial building blocks in the ancient past, digesting them so thoroughly that only their thoroughly mixed stars remain in the halo. This idea turns our search for the missing satellites into a new kind of forensic challenge. Instead of looking for intact dwarf galaxies, we must now search for their faint, dissolved ghosts within the sea of halo stars. This is where the incredible precision of modern stellar surveys becomes essential. Astronomers are now sifting through data on the motions and chemistries of millions of halo stars, hunting for subtle statistical overdensities, tiny groupings that could be the last coherent remnants of a dwarf galaxy that was torn apart 10 billion years ago. Finding these ultra-faint relics is like trying to spot the distinct brushstrokes of a single artist in a painting that has been painted over by dozens of others. The implications of this search reach far beyond our own galactic backyard. If the missing satellites were indeed consumed, it tells us something profound about the nature of the dark matter that shapes them. Certain models of dark matter predict it should be cold, forming many small, dense clumps from the very beginning of the universe, perfect seeds for those numerous dwarf galaxies. If we confirm that our galaxy's halo contains the fossilized stars from hundreds of such clumps, it would be a strong vote for that cold, dark matter model. Conversely, if the halo seems to have fewer progenitor building blocks than expected, it might suggest dark matter behaves differently on small scales, perhaps being warmer and less prone to forming such tiny structures. This is the beautiful, interconnected nature of cosmic science, the forensic history of our own galaxy, written in the motions of ancient stars, becomes a direct test for our most fundamental theories of the universe's composition and birth. The quiet, patient work of mapping stellar streams and tagging chemical families is not just about writing a biography, it is about running a grand experiment on the nature of reality itself. The future of galactic archaeology is arriving, and it will be seen through the eyes of giants. The coming decade will witness the launch and operation of observatories so powerful they will transform our fuzzy, incomplete map of the halo into a crystal-clear portrait. At the forefront is the Nancy Grace Roman Space Telescope, a wide-field instrument that will peer into the infrared. This allows it to see straight through the Milky Way's obscuring dust, revealing the faint populations of stars hidden behind the brilliant disk for the very first time. Roman will conduct a massive survey of the galactic bulge and halo, identifying countless new stellar streams and faint dwarf galaxies that have remained invisible to optical telescopes. It will be like turning on a light in a dark, cluttered attic, suddenly illuminating treasures we only knew were there from the echoes they made, on the ground in the clear skies of Chile, the Vera Sea. Rubin Observatory will begin its legacy survey of space and time. This 10-year project will scan the entire visible sky every few nights, creating the deepest, widest movie of the universe ever made. For our galactic story, its power lies in detection. Rubin's immense mirror and massive camera will find millions upon millions of faint stars in the outer halo, tracing the gossamer thin streams we currently see only in fragments into continuous, delicate ribbons that may stretch fully around the galaxy. It will find streams so faint they are currently just theoretical predictions, the dissolved remains of the smallest and earliest building blocks, but finding these stars is only the first step. To tell their stories, we need to know their chemistry. That is where the next generation of massive spectroscopic surveys comes in. Future missions, building on the work of APOGEE and GALAH, will use dedicated instruments on large telescopes to capture the chemical fingerprints of tens of millions of stars identified by Roman and Rubin. This combination is the complete toolkit. One set of telescopes finds the stars and maps their motions with breathtaking precision, while the other decodes their elemental origins. Together, they will allow scientists to do something extraordinary, not just find a stellar stream, but read its full biography from motion to birth composition. The halo map will evolve from a rough sketch with a few major features into a high-definition image teeming with detail, potentially revealing dozens of previously unknown streams and clarifying the precise sequence and timing of ancient mergers. We are on the cusp of a golden age for this science, where the family tree of the Milky Way will grow from a few strong branches into a lush, detailed canopy, connecting us more directly than ever to the universe's formative years. This cosmic detective story is not just for those with a PhD and access to a telescope. The search for our galaxy's lost history is a project where you can play a direct role. Across the globe, a revolution in citizen science is underway, inviting the public to become active participants in galactic archaeology. Massive surveys like Gaia and the future Vera Rubin Observatory produce datasets so enormous that even the most advanced supercomputers struggle to process everything. This is where the unique power of the human brain becomes invaluable. Our innate talent for pattern recognition, for spotting the subtle and unexpected, can still outperform even the cleverest algorithms. Projects like Hubble Asteroid Hunter have already shown how volunteers can comb through archival space telescope images to identify faint, moving asteroids. That same principle is now being applied to the stars. Upcoming initiatives will ask volunteers to help scan images and data visualizations, looking for the faint, telltale smears of undiscovered stellar streams or unusual groupings of stars moving against the galactic flow. By classifying these features, everyday people can help flag potential discoveries for professional astronomers to investigate further. This process democratizes science in a profound way. It transforms the audience from passive viewers into active co-discoverers. With just a computer and an internet connection, anyone with curiosity can sit down and help sift through the raw data of our galaxy's past, potentially uncovering a stream that points to a forgotten merger. It forges a direct, personal connection between you and the cosmic story being told, reminding us that the quest to understand our place in the universe is, and always has been, a deeply human endeavor shared by all. This knowledge reshapes something far deeper than our scientific models. It transforms our very sense of place. For most of human history, the starry vault above was the ultimate symbol of permanence. The constellations were fixed, the Milky Way a timeless, unchanging river of light. Our myths spoke of celestial spheres and eternal heavens. That perception is now irrevocably altered. We do not live within a static, finished cathedral of stars. We are riding inside an ongoing construction site, a dynamic entity with a violent biography and an even more dramatic future. The ground beneath our feet, or rather, the galactic plane that cradles our solar system, is built upon the merged remains of other worlds that once shone independently. This realization carries a profound philosophical weight. It dismantles the illusion of cosmic permanence and replaces it with a narrative of continuous, majestic change. We are not simply inhabitants of a galaxy, we are witnesses to and products of its evolution. The atoms that form our planet and our cells were likely forged in the stellar furnaces of multiple galactic lineages, stirred together by collisions that occurred billions of years before the Sun was born. Our existence is intertwined with these ancient cataclysms, not as destruction, but as a necessary creative process. This perspective connects us to a timescale that dwarfs all of human history, a deep time narrative written in the motions of stars. It fosters a humbling yet exhilarating sense of connection. We are not passive observers looking out at a distant, finished universe. We are active participants within a living, breathing cosmic story, one where the past is still visible in the halo and the next chapter is already written in the gravitational dance with Andromeda. It suggests that change and transformation are not merely earthly experiences, but fundamental principles woven into the fabric of the cosmos itself. Our galaxy's life story can now be read like chapters in a book, a violent biography written across more than 13 billion years. It begins in the profound darkness following the Big Bang, as slight ripples in the fabric of spacetime cause dark matter and primordial gas to condense into the first fragile clumps. From this cosmic seed, the infant Milky Way began to coalesce. The earliest chapters are the faintest, hinting at a possible first colossal merger with a galaxy astronomers call the Kraken, an event so ancient its evidence is nearly erased. Then, around 10 billion years ago, came the defining collision. A massive dwarf galaxy, now known as Gaia-Enceladus, slammed into our young galactic home in a head-on impact that fundamentally reshaped its structure, triggering immense waves of star formation and building its thick disk and inner halo. Not long after, another building block arrived from an unusual angle. Its stars deposited into the looping orbits we call the Helmi stream, adding another distinct layer to the growing galactic fossil record. For billions of years that followed, the assembly continued at a steadier pace, a diet of smaller snacks that steadily enriched the halo. Then, relatively recently in cosmic terms, a new character entered the scene. The Sagittarius dwarf galaxy began its long, doomed spiraling dance with the Milky Way, a process of tidal dissolution we are witnessing in real time as its stars rain down into the great stream that bears its name. This ongoing digestion is a preview of our immediate future, for the next major act is already in motion. The large Magellanic cloud, that bright southern smudge, is not a permanent satellite but a first-time visitor, currently falling toward us and destined to be torn apart and absorbed over the coming eons. And finally, the ultimate chapter has been preordained by gravity itself. In roughly 4.5 billion years, our Milky Way will meet its sister spiral, the Andromeda Galaxy, in a merger of equals. This transformative event will erase the two majestic spirals and forge a new, elliptical galaxy, an entity for which we have already chosen a name, Milkdromeda. This consolidated timeline from the Kraken to Milkdromeda is not just a list of events. It is the singular narrative arc of our home, a story of continuous construction and change that turns the static sky into a living, evolving pageant. The serene spiral we call home is a cosmic mosaic assembled from the remains of countless others. This is the core revelation of galactic archaeology, that our Milky Way's majestic beauty is the direct product of a relentless billion-year history of consumption. Its peaceful appearance is an illusion of timescale, masking a dynamic biography written in the silent language of stellar motion and ancient chemistry. We have traced this story from the colossal Gaia-Enceladus merger to the faint whispers of the Kraken, from the real-time dissolution of Sagittarius to the impending arrival of the large Magellanic cloud. Each event was not a moment of chaotic destruction, but a structured, fundamental process of growth and assembly, governed by the immutable laws of gravity. This violent past was the necessary creative force that stirred the galactic pot, enriched it with the elements for planets, and ultimately sculpted the specific galactic neighborhood that cradled our solar system into being. Our journey has taken us from forensic discovery in vast stellar datasets to a deeper philosophical meaning. We are no longer just inhabitants of a galaxy. We have become its historians, learning to read the layered narrative of our own origin. This knowledge forever changes the night sky. The next time you look up at that hazy band of light, try to see beyond the simple beauty. See the great looping river of the Sagittarius stream, a galaxy being unraveled before our eyes. See the halo not as empty darkness, but as a crowded archive, glittering with the orphaned stars of lost galaxies. See the faint smudge of the large Magellanic cloud, and know you are witnessing the first chapter of our galaxy's next major meal. And let your gaze drift toward Andromeda, understanding it is not just a neighbor, but our future. The sky is no longer a static painting, it is a living, evolving story, and we are now privileged to read its pages. If you found this deep dive into our cosmic home compelling, consider subscribing for more journeys to the heart of the universe's greatest mysteries. We would love to hear your thoughts on this galactic saga, so please share your reflections in the comments below.